Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast is going to cover separation and purification techniques. I'm going to focus on kind of three categories. That is the separation and purification of organic molecules. And then I'll talk about separation and purification of proteins. And then lastly, I'll go into the separation and purification of cells. And so you're mainly going to see this material come up in 2 out of the 4 MCAT sections. Those sections would be the biochem section and the phys-chem section. Of course, you'll see probably in the phys-chem section more of the organic molecule separation, purification, and then probably in the biochem section, you'll see more of the protein stuff. And I threw in this cell separation and purification techniques because it's interesting and, I haven't seen it too much on the MCAT, but I could definitely see them throwing it into the biochem section. So just keep that in mind. All this stuff is pretty important. It'll bring you back to OChem lab, biochem, a lot of these different lab classes, but definitely have seen these come up on the MCAT, so it's important. I hope you learned something that you didn't know before. It'll help you on the MCAT. So let's get started. All right, the first thing I want to get into here is organic chemistry and chemistry separation and purification techniques. So I'm going to talk about extraction, I'm going to talk about crystallization, and then I'm going to talk about chromatography. And in terms of chromatography, I'll talk about thin layer chromatography and then also HPLC, which is high pressure liquid chromatography. All right, so let's talk first about extraction. So extraction is a separation of chemical compounds using their differing solubility properties in different liquids. And so there's a few different kinds. There's liquid extraction, there's liquid-solid extraction, which is my favorite form of extraction because that is how you extract caffeine from coffee. I'm going to first focus on liquid extraction. So liquid extractions rely on what's known as solvent partitioning. That basically means that compounds have different solubilities in 2 different solvents. And so what happens is you use one solvent to essentially pull out these compounds from another solvent. And this relies on the fact that in this second solvent, these compounds are more soluble. So they're able to dissolve better in one solvent, and therefore you extract that compound to the other solvent. And so let me give you a quick example of how this works. So say that I am me and I have a mixture of creatine and caffeine in water. And I know that caffeine is a lot more soluble in water than creatine is. And I also know that creatine is actually much more soluble in oil than caffeine is. And so I have this mixture in water and I start to realize, shit, I already took my caffeine for the day. My caffeine total is at the highest. I had like 3 cups of coffee this morning. I don't want to take that caffeine, but I do want to take the creatine. And so what I decide to do is I decide to exploit these solubilities. So what I do is I take my mixture of these 2 compounds in water and I dump in some oil. And then I shake that water bottle. Let's just say it's in a water bottle. In OChem, you might remember these separatory funnels that were kind of big at the top, got skinny at the bottom, and they had this stopcock you could open and close. But let's just say I have a water bottle. So I add this oil, I shake them up. I have these 2 different phases, one of which is aqueous phase, which is water. The other is a hydrocarbon phase, which is oil. So I shake and then I let it sit. And what happens after a little bit is these phases separate. Right now you have oil phase separate from the aqueous phase, kind of like a salad dressing bottle. And now these compounds have actually partitioned to these different phases. So creatine, a lot more soluble in oil, therefore it's going to be really enriched in the oil phase. And caffeine, a lot more soluble in water, is going to be in that aqueous water phase. And so the only step left now is to then separate these phases. And if you have a separatory funnel, this is easy. You just open the stopcock, wait until you have let out all the aqueous phase. And again, remember the aqueous phase is going to be in the bottom because water is a little bit more dense than oil. I think oil has a specific gravity around 0.9, where water is 1. So you have that aqueous phase in the bottom. You can open up that stopcock and just let that stuff flow out. But if you're in my case, right, I want the creatine from the oil-rich phase, and I use my water bottle to do this extraction, so I don't have this little stopcock mechanism. So what do? So I take my water bottle, I open it up, and I slowly pour out this oil phase until it's extracted from the water. And then I take a shot of creatine-rich oil, and then I call it a day. And so that's just kind of, an off-the-cuff example of liquid extraction. You might be more familiar with step 3A-1 of making methamphetamine, where you use a liquid extraction of methyl hydrobromine dioxide into diethyl ether. You're probably a little bit more familiar with that. But if you like to lift, like to work out, you may be familiar with the case before this. All jokes aside, liquid extraction is a process where you're taking a mixture of two compounds and you are exposing these compounds to a new solvent in which one of these compounds is more soluble than the other in, and then you are having that compound partition into that other solvent, and then you are extracting that solvent alone from the mixture of two solvents. So in this case, these solvents need to be immiscible or, can't mix. And then you extract that one solvent that is now going to be enriched in whatever compound you have. So this method relies on differing solubilities of two compounds that are in a mixture. All right, so let's quickly switch gears and talk about liquid-solid extraction. So this uses the same principle as liquid-liquid extraction, but now you are extracting some compound from a solid. So, the one to really think about here is coffee beans. So what do you do when you are putting hot water into ground up coffee beans? Well, you're extracting obviously some of the, black beans. I don't really know what that is, but you're really extracting caffeine from these coffee beans. And so what you do is you are adding a liquid in which a compound partitions into or is dissolvable in, and you are essentially pulling that out of a solid. Again, this method relies on a compound's solubility in a certain solvent. This time with this solid, it's a little bit less complicated though, because all you're doing is you are dissolving a compound from a solid into a liquid. A little bit more simple. The last method of extraction that I want to talk about here, and one you may have not actually heard of before, is called acid-base extraction. And so as you may be thinking, or as you may have guessed, or as you may have known, acid-base extraction is typically used to separate organic compounds from each other based on their acid-base properties. So it works by the following principle. So generally speaking, organic compounds are more soluble in organic solvents. This makes sense, right? However, if organic compounds are rendered charged, as in an acid-base reaction, let's say at a low pH, some molecule is charged, then it becomes more soluble in water than it does in an organic solvent. So this is the principle that kind of underlies this acid-base extraction. So let's talk about this in terms of like actual organic molecules. So let's say we have some organic molecule A and it's mixed with organic molecule B in some organic solvent. And so they're both pretty soluble in this organic solvent. They're both floating around. And what you really want to do is you want to separate these two molecules out. So let's say that compound A has a pKa of 4. And so in other words, what that means is that under very acidic conditions, it becomes negatively charged. And therefore, based on the principle I was just talking about, will be more soluble in water. However, on the other hand, compound B is neutral and doesn't really react with acids and bases. So what can I do to separate these? Well, what I can do is I can actually throw in some acidic aqueous phase. It's got to be pretty acidic. I think, let's say it's got a pH of 3. And so what happens now is that I mix these phases up. I shake my separatory funnel, and this compound A reacts in this acid-base reaction and becomes negatively charged. Now, that's a lot more soluble in water, so a lot more of those molecules start dissolving in the water, and now I have actually separated A, which goes into the aqueous phase, because now it's charged, from this B molecule that doesn't really react with acids or bases. And so now I can twist my stopcock, and now A shoots out the bottom in this aqueous phase, and now I've separated A from B based on acid-base extraction. And so for the most part, extraction is a separation technique, right? You're separating two molecules. Let's talk now about a purification technique, which is known as crystallization, and then also mention recrystallization. All right, so let's just say that you are a cancer researcher. Put your mind in the brain of a cancer researcher. You have developed this new chemotherapy drug, and the only problem is that you need to isolate this from a bunch of solids, a bunch of junk that is in solution with your new chemotherapy drug. So what you do is you first of all heat up this mixture. It's got your drug in it that you want. It's got all these solid impurities in it, but you just start heating it up. And then what you do as you heat this up is you start to dissolve all these solids. So you slowly dissolve everything. Okay, everything's good and dissolved. So now you have this mixture with all these solubilized solids. And right now it's just clear because you got all these impurities, drugs, all that stuff is dissolved. And now what you do is you quickly cool this really hot mixture by placing it on ice. And if you remember back to OChem lab, you probably did this in one of those like round bottom flasks. But you just take it off the Bunsen burner, boom, set it in some ice. And what happens is that as your mixture cools really quickly, it starts to form crystals of your drug. And sometimes you might form some crystal impurities. And so you don't get rid of all the impurities doing this, but this is kind of the first step of purifying your drug. So when you cool this, crystals of your drug start to form, and then you also start to get some solid impurities, but mostly crystals of your drug. And so you are able to actually leave some of these impurities behind that were present in solution before. And so now what you do is, if you remember from OChem lab, you're going to take the crystal that you produced and you're going to throw it into a vacuum filter. So basically you're going to get rid of this liquid that still contains some of the impurities that you don't want. All right, so what do we have at this step? Well, we have these crystals that are pretty pure, but they still have some impurities. So what do you want to do? You want to recrystallize. And so this brings up kind of an important point to understand. Crystallization is kind of an isolation or crude purification process, whereas recrystallization really purifies your products, gets rid of a lot of impurities, and maybe gets your purity to like 99%. So crystallization is a process that comes before recrystallization that leads to a very clean product. And so real quick, let me just kind of explain what's going on during recrystallization. So, as I said, recrystallization is a step used to purify the compound received from crystallization. And this is more of a purification step. So what you do is you take these crystals that were isolated during the crystallization step, and now you expose them to a new solvent. And what's really important here is that this solvent actually has a really low solubility for your drug. So it's kind of designed in order to have a high solubility for any of these impurities that are in your mixture, but have a low solubility for your drug. And why is this? Well, this is because you don't want your impurities to recrystallize back with your product. And if these impurities have a really high solubility within this new solvent, then they're not going to crystallize. And essentially, you're just going to get pure crystals of your molecule. And everything else here is pretty much the same process. You're using a vacuum filter then to remove the liquid from these crystals, and you dry out the crystals, and then you can do whatever you want. In the case of this chemotherapy drug, you are now going to probably dissolve this in some kind of pure buffer or something that's going to keep it safe so that it can then be injected into cancer patients, and you are going to save lives. And so one thing that I think is kind of interesting here is to think about why the impurities don't form crystals with your new drug. And this is because essentially that pure compounds form these really ordered crystals and don't allow these impurity molecules to actually fit into the crystal, right? The impurity molecule might kind of come in and try to fit in, but like similar to an amino acid that comes into the A site. If that codon doesn't match up, it's going to float away because it's not a fit. So in the same way, these impurities might come in and not be able to fit, and so they don't grow into that crystal. However, when your drug molecule comes into the crystal, it fits perfectly in there like a lock and key, #enzyme, and you form a crystal, which is just a super highly ordered structure. And so before I move on to chromatography, I briefly want to mention the fact that recrystallization, crystallization, and also extraction all rely on solubility. So solubility is very important for being able to purify, separate, and isolate molecules. All right, so as I alluded to, the next type of separation I want to talk about is separation using chromatography. And so chromatography is kind of a very general separation term, right? You might be thinking, okay, you're talking about protein chromatography, organic molecule chromatography, and there's a million different kinds. Well, what are you talking about? Well, here I'm going to talk about two different types. The first is thin layer chromatography. The second is HPLC, which is high performance liquid chromatography. And the general principle here is that you pass a mobile phase through a column or through a plate, and the components of some mixture separate based on the speed that they travel through the column or up the plate. And going back to OChem, I'm sure you remember thin layer chromatography, so that's where we will start. So thin layer chromatography, or TLC, shout out Waterfalls, is a method used to separate different components of a mixture, i.e. you have 2 or 3 solids in a mixture, you use this to separate them and identify them. Unlike extraction though, this method doesn't isolate different compounds. Instead, you're just identifying the presence of certain compounds. And I'll get into what exactly I mean. Just know here, it's not quite like extraction where I actually have in hand a bunch of whatever compound that I just separated. So the setup for thin layer chromatography is like this. So you have a little rectangular sheet of aluminum that's coated in silica usually, some kind of just absorbent material that is usually very polar. And this is considered the stationary phase. And what you do is you put a little small dot of the reaction mixture that you just produced. And so it's got the compound you're interested in and probably a bunch of other impurities or, off-target products. Whatever it may be, you place a dot of your reaction mixture at the very bottom of this plate. Now you take this plate that again is alumina, usually coated in some kind of absorbent material, silica, let's just say in this case. You take that with the dot of your reaction mixture and you place it in some kind of nonpolar solvent. And you make sure here that the solvent doesn't touch your little dot that you just put of your reaction. You probably remember that part from OChem. And what's going to happen is that through capillary action, your solvent is actually going to start running up your plate. And as it runs up the plate, it's going to pick up these different compounds, and these compounds are going to move at different rates up this plate. And what's really important to understand for the MCAT is what determines this rate of movement, i.e., what type of molecules move fastest up this plate and what type of molecules move slowest. Well, the answer to that question is polarity. So the more polar a molecule in this system, the slower it will travel, and the less polar a compound, the more it will travel. And it's very important here you understand why that is. So if you have a very polar molecule, what's going to happen is it's going to be attracted to the very polar silica layer that's on that aluminum plate. And it's not going to move very far in this nonpolar solvent, right? This nonpolar solvent is moving up this plate and it's trying to pull that really polar molecule with it, but it can't because that's kind of sticking to that plate, so it doesn't move very far. However, if you have a nonpolar molecule, then it won't be as sticky to that plate and it will kind of freely move with that nonpolar solvent. And so this movement up the plate is actually quantified by a variable known as the RF, which you also probably remember from OChem. And the RF stands for Retardation Factor, and it is the distance traveled by the substance divided by the distance traveled by the solvent or mobile phase. In other words, if a molecule has a low RF, that means it's pretty polar because it didn't travel very far, obviously. And if a molecule has a high RF, that means it traveled basically as far as the solvent front, and therefore it's nonpolar. So what's the biggest this number can be? Well, the biggest the RF can be is 1, right? Which means that this molecule would travel just as far as the solvent. So that's just important to remember, is the RF goes between 0 and 1. All right, so to summarize all that information, what thin layer chromatography does is it tells you how polar a molecule is. And furthermore, it separates molecules based on their polarity. And what it's really used for, again, I've said this a million times, but it probably reminds you of OChem. What you do is you put a dot of a pure compound that you know is 100% pure, or like 99.9, and you run that right alongside your mixture. And then what happens is you can then compare the RFs of your reaction mixture to the pure compound, and you can see if, number one, you have the compound of interest within your reaction mixture, and number two, what other compounds may be inside of that reaction mixture. And then you can also use it to confirm the purity of some separation technique. Maybe you did crystallization and recrystallization, and you need to confirm the purity of this technique or this method. So you can use it for a bunch of different things, and it relies on the principle that molecules that are polar will be more attracted to a polar stationary phase and therefore not move as far up a TLC plate. And before I move on to HPLC, I want to briefly mention a little asterisk I have to what I just talked about. And the asterisk is that solvents can either be polar or nonpolar. So this is something to kind of keep in mind. The difference in polar versus nonpolar solvents is that polar solvents will actually produce bigger RF values. And so you can imagine that you are some polar molecule and you're trying to absorb to this silica plate, right? It's pulling you down and you're absorbing to it. However, if you have a polar solvent, that polar solvent's also going to start pulling you along the plate too because of intramolecular attractions. So the more polar solvent, the more pull a polar molecule will feel up the plate, and therefore it will have a greater RF. So the big thing to really take away there is that the more polar a solvent is, the bigger the RF values will be. Hence, the further a molecule will travel up the plate. All right, let's move on and talk about high-performance liquid chromatography, or HPLC. And so HPLC is used more in the lab setting, and I don't mean like OChem lab, I mean lab. And so it's a very, very sensitive way of determining what a mixture of compounds is made up of. And how sensitive is it? Well, it can identify trace chemicals in parts per trillion, meaning that if you have one molecule of A and a trillion molecules of B, you still should be able to detect that molecule A. And just to put that in perspective, this is essentially like taking 10 million people, shaving all their heads, laying out all their hair follicles, and then going to one hair follicle, picking it up, and being able to tell me, the exact person it came from and the exact location on that person's head where it came from, starting from 10 million people. So it's a very, very sensitive method, great for the research lab setting. And so HPLC operates on a very similar principle to thin layer chromatography. The main differences with HPLC is, number one, that it operates at high pressure. And so you can think of HPLC as high pressure liquid chromatography, if that kind of helps you remember. And then the other big difference is that it is run within a column. So you have this column that is packed with this adsorbent material. And this is typically silica, as I just talked about. And there are these really, really small, fine particles that kind of fill up this column. And what happens is that you pass some mobile phase, again with a mixture of components in it, through this stationary phase, which is these little teeny packed particles of silica. And the more polar a compound, the more it interacts with these silica particles, and therefore the slower it moves through this column. And as compounds move through this column, they kind of slowly separate, and then they exit the column at different times, and therefore you have separated these different compounds, again based on their polarity. And one thing you should know for the MCAT is the HPLC technique I just described is called normal phase HPLC. And it's called normal phase because the particles within this column are silica and they're polar, and therefore nonpolar compounds will pass more quickly through this column. But what's more common than normal phase HPLC is reverse phase HPLC. And that means that these particles that are within the column have been modified so that they are nonpolar, and therefore they are more attracted to nonpolar molecules. So what does that mean? Well, that means that nonpolar molecules will travel slower through the column and will elute last, meaning that polar molecules will travel the fastest through the column and will elute first. So let me quickly just summarize this for you. So for reverse phase HPLC, you have a stationary phase, which is, again, these little particles that are packed in a column, that is nonpolar, meaning that nonpolar molecules will be attracted and they will travel slower through this column, whereas polar molecules will travel the fastest and elute first. And then in normal phase HPLC, you will have a stationary phase that's polar, that attracts polar molecules, meaning that nonpolar molecules will travel fastest and therefore elute first. All right, so that is HPLC. Before I move on to the next thing, which is going to be protein-based separation and purification, you need to know that in HPLC, at the end of these columns, you're going to have some kind of detector, right? You're going to have to be able to tell which molecule is coming out. You don't really have a comparison like you do in TLC, where you can have, a pure compound running through, so you know exactly what that's going to look like. Instead, usually they have some kind of detector that's like a mass spectrometer or something like that at the end, where you can tell what's coming out the back. And just as a quick example, HPLC is used for testing athletes' urine to see if there's any performance-enhancing drugs, steroids in the urine. They can detect very trace amounts of these steroids or other performance-enhancing drugs, from anything from baseball to football to biking. Lance Armstrong probably took an HPLC urine test, of which was inconclusive because he actually never got caught from a test like this. Instead, he admitted it on Oprah's show. I think was the first time that was officially okay, Lance Armstrong did drugs. But anyways, so HPLC is a very sensitive technique to separate compounds, even down to very trace amounts. All right, so that's a little bit on separating chemical compounds. I think the really big techniques to remember are extraction and then thin layer chromatography. I think those are the two that I've actually seen on the MCAT. But of course, it can throw anything at you, so just be prepared. The next thing I'm going to talk about here is protein separation and isolation techniques. All right, so this next segment is going to be about protein-based separation and purification techniques. And so the way I kind of want you to think about this is I want you to think about the differences between proteins. What are these differences that we can then exploit to separate, isolate, purify proteins? So there's a few different exploitable characteristics of proteins. That is their size, their shape, their net charge, their hydrophobicity, and also their affinity to other molecules. So those are kind of just the basic factors that we are going to use in all of these different techniques to either purify, separate, or isolate a specific protein.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
So there's a few different techniques I'm going to discuss. The first is SDS-page. The second is protein precipitation. And then the last is chromatography. And within the kind of umbrella category of chromatography, there's 3 different types you should really know for the MCAT. That is size-exclusion chromatography, affinity chromatography, and ion exchange chromatography. So the first thing I'm going to get into is SDS-page. So SDS stands for sodium dodecyl sulfate, which is a detergent that essentially denatures proteins and makes them unfold so they become these linear protein chains. Imagine taking like a wadded up piece of paper, unfolding it into a flat piece of paper. That's basically how this detergent works. And then PAGE stands for polyacrylamide gel electrophoresis, which is the part of this process in which you run this protein through a gel that separates the different molecules of protein based on their size. And so SDS-page then is a method that separates proteins based on their mass or their molecular weight. And let me quickly mention why SDS is so important. So if you don't unfold these proteins, then when you run a protein through a gel, right, let's say you have a mixture, you're going to have proteins that, form these perfectly spherical balls, and then maybe some that are more elongated, etc. And so those are going to travel at different rates through this gel based on their shape. So what SDS-page does is it essentially gets rid of that variable. It gets rid of the shape variable because it just unfolds these proteins into these long linear chains. And then that way you can separate them perfectly by their molecular weight or mass. So SDS-page gets rid of the shape variable. Another really important thing SDS-page does is that it gets rid of the charge variable of proteins as well. So in a gel, you apply an electric current to this gel, and what happens is that causes these charged proteins to move through the gel. Well, if you go back to my physics electromagnetism podcast, you'll remember that the more charged a particle is, the greater the force it experiences in an electric field. So if you had 2 proteins and they're the same size, but one was more charged than the other, then in a gel, the one that was more charged would actually travel further down the gel. So what SDS-page does is essentially ensures that each protein has the same negative charge. So this is all to say that SDS functions to remove 2 variables out of separating these proteins. That is the protein's charge and the protein's shape. So again, once these proteins are unfolded by this SDS, you place them in this polyacrylamide gel, and what happens is these smaller proteins move further through the gel. They move further down through this gel, and the bigger proteins don't move as far. And so what happens then is you get the separation of these proteins based on their molecular weight. And so you get distinct bands on the gel, and if you've ever seen any kind of gels that have been run, on DNA or proteins or anything like that in a lab setting, you'll know what I'm talking about, but you get these distinct bands on a gel that correspond to some molecular weight. And if you've never seen this before, I recommend you just go look it up, kind of see what I'm talking about. But usually how this works is you'll have a ladder that's run on the gel, and a ladder is just a set of proteins that have known molecular weights. And so when you run them, you get a bunch of different bands and you know exactly the molecular weight spread of these proteins. So then what you can do is you can run your protein or your mixture of proteins alongside of it. And then from using that ladder, you can estimate the molecular weight of the proteins that you ran through this gel. And so that's the basic principle through which this SDS-page works. What I think is more important for the MCAT is understanding the difference between 3 different types of page. You have reducing SDS-page, non-reducing SDS-page, and native page. And this is really where I've seen it come up on the MCAT. So if you haven't been paying attention so far, pay attention to this part. So non-reducing SDS-page is exactly what I just talked about. You separate proteins based upon their molecular weight. You throw in this SDS, which is detergent, which unfolds the proteins. Then you throw them onto this gel, and then you get bands depending on the molecular weight of these proteins. On the other hand, reducing SDS-page uses a reducing agent to break disulfide bridges between protein subunits. In other words, this pulls apart protein subunits and then unfolds them and then runs them on a gel. So in this case, you are able to look at the size of protein subunits and elucidate whether or not a protein may have subunits or it may not have subunits, right? If you were to have a single protein and then run a reducing SDS-page and you saw the same exact band pattern as you did for a non-reducing SDS-page, well, then you would know that this protein is probably not made up of subunits. And the last page I want to talk about here is native page. And this can also be abbreviated as CN-page, just so you know. And essentially, this type of page does not use detergent, which is why you leave out the SDS part. And instead, it separates protein based on the 3 factors that I was talking about that SDS gets rid of. So it separates proteins based on their size, their charge, and also their shape or their conformation. And at this point, you might be thinking, okay, why the hell would I want to do that? Right? You're separating proteins based on 3 variables together. It's just really confusing. Like, what do you actually get out of running a native page? Well, one place this comes in handy is when you're looking at protein aggregation states. When you don't use SDS, you essentially keep protein aggregates intact, right? You don't break up these aggregates. And so one way to look then at protein aggregation is to run a native page and to see if you get these big kind of high molecular weight bands that come from protein aggregation. So one function of native page is to look at protein aggregation states. So let me just give you a real quick summary of what I just said. So reducing SDS-page uses a reducing agent to break disulfide bonds, which then breaks up protein subunits. And so then you're essentially separating proteins by their subunit and then by their molecular weight. And then non-reducing page, you do not use a reducing agent, so you don't break up a protein in terms of its subunits. You just keep all the subunits together, then separate proteins by their molecular weight. Native page does not use any type of detergent, so you are separating proteins based on their size, their charge, and their shape. All right, so the next purification technique I want to talk about is called protein precipitation. And protein precipitation is used to concentrate and purify proteins. And it works on a pretty simple principle, and that is that you add some kind of compound to a mixture of proteins along with impurities that decreases the solubility of your protein of interest that's in that solution, and you make it less soluble by adding in whatever this compound is. And what that makes it do is it makes the protein that you want or that you're interested in crash out of solution or form these insoluble aggregates. And so there are 3 main compounds that can be used to precipitate proteins, or I guess 3 main categories of compounds. The first of which is salts. The second of which is acids or bases, and this is called isoelectric precipitation. And the third is miscible solvents. And all these methods rely on the same principle pretty much. And that is that they reduce the charge of a protein. So if you think about a bunch of proteins in solution, let's say that they're all negatively charged. Well, what happens when one protein comes in close contact with another protein? Well, if they're the same charge, then they repel. So when you have a bunch of these negatively charged proteins in solution, they are not going to precipitate because they're not going to form aggregates, right? They're going to get close to each other and then they're going to be repelled. And so that kind of maintains their solubility. But let's say you add a salt, which is the first compound that I talked about. So you add some kind of neutral salt to your mixture of proteins. And what happens is that the salt acts to actually shield the charge. So charges on the surface of this protein, which are all negatively charged, are all blocked. And what happens is then that this causes the proteins to no longer repel each other, and then they aggregate and they start forming these bigger and bigger clumps until they are insoluble, and then they start to precipitate out of solution. So salt can shield the charge between proteins, causing them to aggregate. How exactly does isoelectric precipitation do this? Well, as I said before, you can add some kind of acid or base And what that does is changes the pH of the solution these proteins are in. And you change this pH until you reach the pI of the protein. And again, the pI of a protein is the pH in which the net charge of the protein is 0. So again, you're decreasing the charge of the protein until it is 0. And what does that cause the protein to do? Well, it causes the protein to aggregate and crash out of solution. The last additive I mentioned that you can use to precipitate proteins is miscible solvents. So miscible solvents are solvents that are able to fully mix with and dissolve within water. So that's things like ethanol, methanol. Those two can be used and mixed with an aqueous phase to precipitate a protein. And this works in a little bit of a different way than the other two. But basically, this decreases the solvation layer around a protein by replacing this cage of water molecules that forms around a protein and making this protein less soluble. So if you go back to biochem is probably when you talked about this, but you get this cage of water molecules that forms around a lot of these biomolecules that are in solution. You know, they form this kind of ordered cage because of the hydrogen bonding. And so what that tends to do is that tends to solvate molecules. It makes molecules dissolvable. Well, when you add in some kind of miscible solvent like ethanol, that causes those water molecules to be displaced around the exterior of this protein, which causes it to be less solvable, which means that if you add enough of this miscible solvent, you can actually precipitate these proteins and then collect that precipitate, and now you have purified protein. And so a lot of manufactured therapeutic proteins are actually purified this way. You know, take for instance, insulin. You can flocculate insulin or have it flocculate together, which is just say, form these aggregates within solution that are no longer soluble, and you can kind of purify this protein that way. But you can run into problems with this if you have some solution of a protein therapeutic. So say you have insulin, right? It's ready to be injected into a patient that is suffering from diabetes, and you have it in this vial. And so it's pretty stable, right? It's not just going to crash out. But let's just say you do something, maybe you accidentally leave it out in the sun or whatever, and now what happens is some of that protein begins to precipitate from the insulin solution. And so now when this patient goes to inject themselves, the protein concentration in that solution is no longer going to be what it should be, right? Because now you have these solid chunks of protein at the bottom of the vial. And so this patient is not going to get an adequate dose of insulin because it has precipitated within this vial. So again, you can use precipitation to purify proteins, and this basically works on the basis of eliminating repulsions between protein molecules. You can do this using salt, you can do this using changes in pH to get to a protein's pI, or you can do this by adding some kind of miscible solvent. All right, the next protein separation technique I want to talk about here is called isoelectric focusing. And this is kind of similar to the isoelectric precipitation that I talked about. It separates proteins based on their pI, which again, the pI is the pH in which the net charge of a protein is 0. And in my opinion, this is kind of the most elegant technique for separating proteins. It's really pretty cool. So what happens is you have a gel that you run a protein through. Now this gel has a pH gradient throughout it. So in other words, at the very beginning of the gel will have a pH of 10, and then near the end of the gel will have a pH of 1. And in between those points, it's a gradient of pHs, right? You have, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, all the way through the gel. So you place these proteins in the gel, and then you run the proteins through the gel using an electric field. Again, this electric field pushes the charged proteins through the gel. And what happens is, as these proteins travel down this pH gradient gel, they eventually reach a pH in which the pH in this part of the gel is equal to their pI. And at this point, the proteins have no net charge. And so what happens to a particle that has 0 net charge in an electric field? It doesn't feel any force. So at this point, the protein just stops moving right where it's at. And so what happens is if you have a mixture of proteins, they'll all separate based on their differing PIs at different points in the gel. And then you can just cut that part of the gel out. And now you have this specific protein that has been separated based on its PI. Pretty cool, pretty elegant technique. I honestly don't know if this is used a lot in research just because I don't do a lot of protein research, but it seems like a really cool, useful technique and one you'll probably see on the MCAT. All right, the last protein separation and purification technique I want to talk about is chromatography. And so I'm going to talk about 3 different types of protein chromatography, the first being size-exclusion, the second being affinity chromatography, and the third being ion exchange chromatography. And just a heads up, this material is probably the most common on the MCAT out of all the material I've talked about. So know these chromatography methods. You'll definitely see at least one question about this, probably on the biochem section. But just know this stuff's important. The same principle of chromatography that I talked about earlier also applies here. So in general, chromatography is used to separate proteins based on moving a solution with proteins in it, called the mobile phase, through a solid stationary phase. And based on the interactions between this solid stationary phase and proteins in the mobile phase, you get proteins moving through the column at different speeds. So proteins all of the same kind move through the column at the same speed. Different proteins move through the column at different speeds, and then they exit the column at different times, and therefore you are able to separate these proteins. Before I get into size-exclusion chromatography, there's a few terms related to chromatography that you should know. The first is eluent, and this is the liquid that is going into the column. And then you have the eluate, which is the liquid coming out of the column. So those are 2 kind of words to keep in mind. You might see those come up on the MCAT. If not, it'll just help you understand chromatography a little bit better. All right, so size-exclusion chromatography is the first of these chromatographies that I'm going to talk about. It's also kind of the most simple. I guess in my opinion, it's the most simple. And it works like this. So you have a solution with proteins in it. Call this the mobile phase again. And you pass this mobile phase through a column, in this case, a size-exclusion column, that is filled with solid polymer-based beads. And these beads are really, really small, and they all have these pores in them of different sizes. And what these pores do in the beads is they essentially catch the proteins. And so you can imagine that the proteins can kind of float into the pores and float out of the pores. And so there's this process of these proteins going in the pores and coming out of the pores that actually slows these proteins down as they travel through the column. And the principle that it works on is this. The smaller the protein, the more pores this protein can enter, and therefore the longer it takes for the protein to go through the column. On the other hand, if you're a big protein, you just can't fit in many pores, and so you just kind of go through the column pretty fast, right? It's like me trying to fit through doorways. I'm just too freaking jacked to even fit through the doorways. And so a lot of times I end up just going straight through the wall, which is actually faster to my destination than it would be to go through doors. So anyways, for size-exclusion chromatography, bigger proteins move faster through the column, smaller proteins get stuck in these pores, and therefore they travel slower through the column. So in terms of what elutes first, that's going to be the bigger proteins, and what elutes last is going to be the smallest proteins. On the MCAT, you're going to probably see this in the form of a chromatogram. So you'll have something like time or volume eluted on the x-axis, and then on the y-axis, you'll have some kind of quantification of protein. So what it's going to look like is going to look like peaks as you go through time, right? So, I elute, and then all of a sudden a protein comes out all of the same kind because it all takes the same amount of time to go through this column. And then I go on a little bit more time of eluting some of the liquid out of the column until boom, I get another protein that's eluted, and so forth. And so again, these first proteins are going to be the biggest ones, and the last proteins are going to be the smallest ones. It's also important to note you're going to have an exclusion limit. In other words, all the proteins that are above some molecular weight cutoff will actually flow out of the column at the same time. And this is because they literally don't interact with any of the pores at all. So they just flow straight through. So the very first peak on your chromatogram is actually going to include probably more than one protein. And these are going to be all the proteins that are too big to even enter any of these pores. So I've seen that come up on the MCAT. Just make sure you understand how to read a chromatogram. If you don't know what they look like, go look one up. You'll probably see that somewhere on the MCAT. And if you see something called gel filtration chromatography, just know that for all intents and purposes, that is the exact same as size exclusion chromatography. All right, so now moving on to the next type of chromatography that you should know in terms of protein purification and separation, that is affinity chromatography. And so affinity chromatography is a little different in the fact that it is a very highly specific separation. And so you have this mobile phase, which is going to be a solution of proteins, maybe some impurities mixed in. And now you have a stationary phase that is, again, these polymer beads, but this time they are conjugated to some type of molecule called a ligand that actually binds to a very specific protein or a group of proteins that you're interested in separating. And typically these ligands are antibodies or some other kind of protein or some kind of small molecule that kind of specifically binds the protein that you want to use. So for instance, Thermo Fisher Scientific, which is one of the US's largest biotech companies, makes these affinity columns that have antibodies that can bind to very specific types of immunoglobulin. So you have immunoglobulin G, which is IgG, then IgM, etc. And I am going to do an immunology podcast. I think that's going to be my next one, is the immune system. And I'll talk more about these different immunoglobulins there. But anyways, back to the point. So this ligand can be anything that specifically binds to a protein. And the procedure to use an affinity column goes like this. So you pass your eluent through the column, which is, again, your mobile phase that contains your proteins of interest. And you let that eluent kind of sit in this column for a little bit, and that allows the ligand to bind to your protein of interest. And then you wash the column with an inert buffer. That just kind of gets rid of all the excess proteins that didn't bind to the ligand and the other impurities. And then what you do is you elute the column with a buffer that is actually capable of breaking the protein-ligand complex. And then once you do that, you can just elute out your protein of interest and you collect your pure protein that you now separated from other proteins and impurities. Pretty sweet. So the takeaway for affinity columns is that they're able to separate out very specific proteins using some type of ligand that can specifically bind that protein. All right, the last type of protein chromatography I want to talk about is ion exchange chromatography. This one I've seen on the MCAT as well, so pay attention if you are not. Ion exchange chromatography separates proteins on the basis of charge. So again, imagine you have a solution of proteins along with some impurities in a mobile phase. And now you pass this mobile phase through a column that's filled again with beads. This time though, the beads, which are the stationary phase, are charged. So these beads have some charge, and essentially they attract proteins of the opposite charge to themselves and capture those charged proteins as they pass through the column. So for example, say the charge of these chromatography beads is negative, well then you're going to capture all the proteins that are net positive, and everything else that's either uncharged or negatively charged passes through the column and is eluted out. And then of course you need to be able to recover these proteins that you just trapped with these charged beads. So what do? You pass through a buffer that has high ionic strength. In other words, you have a bunch of extra ions floating around, plus charges, minus charges, whatever. And what this does is that these charges interact with the beads and essentially kick the proteins off the beads and then allow the proteins to be eluted and separated. And now you have separated proteins based on their charge. All right, so that's kind of an intro into a few types of protein purification and separation chromatography. The first thing I talked about was size-exclusion chromatography, and that just separates proteins based on their molecular weight or their size. The larger proteins elute out the column first because they're not able to make it into these little pores. Next, we had affinity chromatography, which is a very highly specific type of chromatography where we have some ligand bound to a bead that's able to capture these very specific proteins. And then the last thing I talked about was ion exchange chromatography, which separates proteins based on their charge using charged beads. Alrighty, so that is protein purification and separation. The next thing I want to talk about is cell separation and purification. So how do you take a mixture of cells and either purify a specific type of cell, get rid of impurities, or sort cells? So I'll talk about a few different methods here. All right, so I'm going to talk about 3 different types of cell separation and purification methods. The first is centrifugation, the second is flow cytometry, and the third is the very general category of microfluidics. But before I get into these, I want to talk about what sets cells apart from both proteins and organic chemicals. What makes them so hard to separate? And that is that they are delicate and sensitive. Right? If you were to run a cell through a chromatography column, it would just tear that cell to bits, right? You might get a little DNA out the end or something like that, but there's no way that you're going to try to pass a cell through a chromatography column and then put that eluate into culture and expect cells to grow, right? They're not going to survive their way through a column. And same with extraction, right? You can kill cells from shaking a flask of cells vigorously. You can kill them. So, one thing to remember about cells is that they are like soccer players, right? They're delicate, they're breakable. You barely kick one in the ankle, they're gonna fall over, roll around, be taken off on a cart. All right, so let's talk first about centrifugation. So let's say that I have a tube of cells and there's some dead ones, there's some live ones, there's some other nasty shit in there that I wanna separate out from the live cells. So what do? Well, what I do is I put that tube in a centrifuge. And a centrifuge is just this device that spins around really, really fast. And so what that's going to do is it's going to apply a centripetal force to particles that are in this tube, i.e. the cells and the debris and all that other stuff. And this force is felt in the direction of the bottom of the tube. So it's going to pull these bits down towards the bottom of the tube. And what exactly is this force felt, or what does this force rely on? Well, let's go back to physics and figure this out. The equation for centripetal force is mv squared over r, where m is mass of the particle, v is the velocity, and r is the radius. And in a centrifuge, it's important to note that all the particles will be at the same velocity and the same radius from the center of the centrifuge. So then what determines the force on these particles? It's just their mass. Just the mass of the particles determines the magnitude of centripetal force that they feel. So that's important to keep in mind. And so each of these particles and cells and dead cells within this tube are going to feel a force that is proportional to their mass. And so it's important to note here that the mass of live cells is greater than that of both dead cells and particulate matter. So what happens is that if you spin these cells, and it's a very specific frequency of rotation, I think like 1100 rotations per minute, something like that, then what happens is you will actually pull down these live cells while leaving the dead cells and the cell fragments and all this other crap up in solution. So you can actually use centrifugation at a very specific rotation frequency to then purify live cells from impurities. And again, this relies on the fact that live cells are more massive than dead cells and these other little impurities. All right, so the next cell separation and purification technique that I want to talk about is called flow cytometry. And flow cytometry is a cell separation method that is commonly used for counting specific cell populations or sorting cells. And in principle, it's a pretty simple method. So what you do first is you stain cells with very specific fluorescently labeled antibodies. And these antibodies bind to different cell surface markers. So for example, CD4 T cells, which are helper T cells, have this CD4 surface marker on the outside of them. So you can add in an CD4 antibody that binds to the CD4 on the cell surface and then fluoresces. And from there, you can actually have a machine that detects this fluorescence and then either counts the cell or can sort the cell. Same thing goes for CD8 T cells, which are known as cytotoxic T cells. So again, you add in this anti-CD8 antibody that binds to this cell surface marker, and then you can count it based on its fluorescence, or you can sort it based on its fluorescence. And this system that's able to sort or count these cells, essentially all it does is it takes these single cells and creates a single file line out of them. And then it passes that single file line of cells through some kind of detector. And what the detector does is then detects the fluorescence of this single cell and either counts it or sorts it right there. So, imagine a line of humans, and as they're walking through a doorway, you're looking at them. You're that detector. You're looking at them, and you're looking for green shirts. So, someone with a blue shirt walks by, a pink shirt, and it keeps going. People are walking by, and then boom, a green shirt. And what you do is you just give them a kick. Kick them right out of line. Just Spartan kick them. Maybe they fall back flat on their back or whatever. But you're detecting those people with green shirts in the same way that the cell sorter system would detect these fluorescently labeled cells. All right, the last technique I want to talk about here is microfluidics. And this is kind of the most cutting edge of the three techniques. It's definitely a hot area in research right now because what it allows you to do is isolate single cells. And essentially how this works is you have two very thin channels that feed into a bigger channel. And in one of these channels is oil, and one of these channels is some kind of aqueous solution. What happens when you mix these is you form these droplets of aqueous phase within oil, or droplets in oil, I'll just call it that. And what you can do then is using these microfluidic devices and a lot of cool engineering that goes on behind them, you can fill each of these aqueous drops with one cell. And then from there, you can kind of transport these aqueous drops around in microfluidics systems to do different things, right? You can put those into a single tube to then do reactions on and study and whatever you want to do. You can run a PCR on that cell right there. You can do a lot of different things. So, this might be a little bit out of the scope of the MCAT, but just understand that microfluidics can be used to isolate single cells and do interesting things to those single cells. Alrighty, so those are three techniques that you can use to separate and purify cells. We have centrifugation, which is probably the most important here, and that is going to help you purify living cells. And then we have flow cytometry, which helps sort different cell populations or count different cell populations using cell surface markers. And then last, we have microfluidics, which is kind of a hot cutting edge technology that can be used to study single cells. So that concludes the Separation and Purification Techniques podcast. Thanks as always for listening. If you have any comments, concerns, feedback, feel free to email me. If you like this podcast, please go give us a review on iTunes. It helps us reach more people and helps our rankings. Be on the lookout for the next podcast, which is going to be on the immune system. Should be an interesting one. You might hear more about CD4, CD8 T cells, maybe a little more about flow cytometry, which you should be excited about. That's all I got. Thanks for listening.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com for the experts.